All right, so now we're going to go ahead and set up this problem that we talked about where we're trying to find the surface integral through these 5 faces, and we've identified that we can use the divergence theorem for the closed cube and then subtract just that extra face that it gives to us. So for our first part, we're just going to do divergence theorem over entire cube. And so that's going to be the closed surface. Unit cubes are just x goes from 0 to 1, y goes from 0 to 1, z goes from 0 to 1. That was given to us in the problem statement. And then we'll do that in a second. And then we're going to think about the surface integral over the bottom. We're going to find this thing. So that's where z equals 0. And then x and y are falling between 0 and 1. And then we're going to subtract the two. So divergence over the entire cube. We better compute our divergence. Our vector field F is continuous. Really is minus c squared. Okay, it's continuous and it's a closed surface. So we can go ahead and look at d dx of the first component was xy plus d dy of the second component was 0. d dz of the third component minus c squared. So d dx of xy is going to give us just y, which is a constant as far as x is concerned. d dy of 0 is 0. And d dz of minus c squared is minus 2z. So this is going to be y minus 2z. And so the integral over the entire cube is the volume integral over the interior of the cube. So x, y, and z all go from 0 to 1 of the divergence. That's just our divergence theorem that we've had a lot of practice using up to this point. I think it should be pretty simple with all the ones. So integral of y minus 2z with respect to z is going to be yz minus z squared, evaluated from 0 to 1. So that just becomes y minus 1 minus 0 minus 0. Integral of y minus 1 is 1/2 y squared minus y, evaluated from 0 to 1. That's just going to give us 1/2 times 1 minus 1 minus 0 minus 0. So that's 1/2 times the integral from 0 to 1 dx. Minus 1/2, 1/2 minus 1. Integral from 0 to 1 dx is just 1, so this is minus 1/2. So this entire thing right there is just that minus 1/2. And then we have to compute the surface integral over the bottom of the cube, this part that we were supposed to leave out, this S6. So our F is xy minus c squared. All right. And then when we set up our surface integrals, we look at f dotted with the normal vector integrated over the surface. And so the surface is going to be this unit square, 0 less than or equal to x less than or equal to 1. And then since we're thinking about this unit square, our normal vector oriented outwards would have been just down. So our n is equal to minus k hat. Our f along the surface is equal to xy 0 and then minus c squared. But this is one of those tricky problems where we're looking at z equal to 0 everywhere on the surface. So minus c squared is just 0. Let me do that in the same notation. So f dot n is going to give us 0 times xy plus 0 times 0 plus minus 1 times 0. And the important part is that that's just going to give us 0. So the surface integral is 0 over the area. So you could do 0 times the area, but that's just going to be 0. So there actually is no flux through that bottom part of the cube. So that S6 surface integral through the bottom of the cube is 0. So the flux through the other 5 sides is actually just minus a half. So we had this formula, it would be the result of the divergence theorem minus the flux through that last surface. So we got the minus a half minus 0 is just minus a half for the final answer. And that's how you can set up a divergence theorem problem over an open surface.